more about pressure and temperature from a molecular view. And we'll also talk about volume too. So in chemistry and the sciences in general, there's a branch of it that attempts to relate macroscopic variables such as pressure and volume and temperature, things we can measure for normal size samples, things we use every day, relating them to atomic properties. And so I will not do a complete derivation, but I will give you a flavor for how you relate atomic or molecular or particle scale properties to variables that we can measure macroscopically in our everyday lives. To do that, we're going to calculate the pressure of a particle hitting a wall, and we're going to do it for one particle in a box, and the box has length L. It has area A on this end, and we have one particle with mass m, and that particle is moving in the x direction with a velocity v sub x. So this is the x direction. Now, the force of a collision of a particle is, for anything, force equals m times a. That's mass times acceleration. So m equals mass, a equals acceleration. And if you've taken a physics class, then you know that acceleration is change in velocity over change in time, where v is velocity and t is time. And the capital Greek letter delta means change. And what we're going to say is that this particle, when it has a collision, the force of that collision is going to be the change, the acceleration is going to be delta v over delta t, and the delta v, when there's a collision, is going to be vx, and then it's going to be minus vx, because the change, and these r vectors, means that the direction is changing as well, and you end up with 2v, or 2vx in this case. That's going to be delta v, the change in velocity of the particle when there is a collision. Now, the collision occurs every delta t, and delta t is the time between collisions. And the time between collisions, well, it bumps into this wall, then it's going to go down and then come back. And since the length of this between collisions is going to be L and then another L, so that's 2L, and it's going to take an amount of time to get back divided by the the velocity. So 2L over Vx, where Vx is in the denominator of the denominator. And what we can do is, just by talking about a particle in a box with mass m, we can see that its acceleration is going to be, well, the 2's cancel, and we get Vx squared over L. That's our acceleration. We now know delta V over delta T times m is going to be mass times Vx squared over L. And the only thing we haven't talked about now is that this is going to be an average velocity when we talk about more than one particle or more than one collision. Now, to take it one step farther, we've previously said that the pressure is going to equal force over area. And so the area of the wall is A. Either wall is A, by the way. And so mass times average velocity in the x direction squared over L times A, where L times A is going to be the volume of the container. So now we have velocity in the x direction, average, and volume here. And we can keep going along these lines. We can see that mv squared, v average squared, is going to be related to the temperature. And we have said previously that mass times velocity squared is proportional to temperature. So we can say P is proportional to T over V, where we take and put in the proportionality. And we're starting to get something that looks like the combined gas law. And P, V, and T are macroscopic properties that we can measure, and the mass of a particle and the velocity is a microscopic or atomic property that we could start thinking about what are those velocities. And that's where we'll stop. All I want to motivate for you is that there are ways to relate macroscopic and atomic properties by setting up very well-defined systems. And from there, and it's a long ways, you can get an equation for the velocity or the root mean square velocity of a gas particle. And the velocity root mean square is going to be the root of 3 times r times t over molar mass. So mm equals molar mass. R is the ideal gas constant, and R previously has been 0.08206, and that was in liter atmospheres per mole Kelvin. There's another value of R. It is 8.314 joules per mole Kelvin. And that's the version of R that we will use in all cases other than the ideal gas law. The R value we've been using, 0.08206, that's going to be only for the ideal gas law moving forward. I'll point out that the molar mass in this equation, since we're talking about joules, and we're going to talk a lot more about joules in the next unit, but molar mass in kilograms per mole instead of grams per mole. And that will make our units cancel very nicely, as we will see in future lectures when we talk about that. So what this means is we have an equation for the root mean square velocity, and what we will treat it as is essentially the average or close to the average velocity of a gas phase particles. For example, what is the root mean square velocity of a molecule of oxygen at 0 degrees Celsius? It's going to be 3R, which is 8.314 joules per mole Kelvin, times temperature in Kelvin, so 273 is 0 degrees Celsius, divided by the molar mass of oxygen. Well, it's 32.00 grams per mole. To make it into kilograms, you can either do the unit conversion specifically using something like a picket fence, or you can realize that grams to kilograms is a factor of 1,000. Like so. And what we get here, if we multiply it out, it's going to be 3 times 8.314 times 273 divided by 0.032, and then take the square root of the whole thing. For mine, it's shift second here. I get 461 for my number. We can talk about units, or we can just accept the fact that this comes out as meters per second. And, well, let's go ahead and talk a little bit more about that. We can see that our moles cancel, we can see that our kelvins cancel, and we are left with joules per kilogram. It turns out that 1 joule equals 1 kilogram meter squared per second squared. And this comes from the fact, or is, let's say this is related to the fact that kinetic energy equals 1/2 mv squared, where mass is in kilograms and velocity is in meter per second, which is then squared. That's what I always think of when I think of units and the relationship between what is a joule and how is it defined in SI units. So a joule per kilogram cancels out the kilogram. And I should say the units should be square rooted there. Because then if you take away the kilograms here, you're left with meters squared per second squared, which is just meters per second. Fun to think about, not necessary on the exam. Here's a companion problem for you to work. Make sure you figure out the molar mass of propane and then convert it to kilograms per mole. Well, now let's talk about diffusion and effusion. So the process of a collection of molecules spreading out from high concentration to low concentration is called diffusion. And really, diffusion and effusion are very related, as we will see, even though they are different processes. The process by which a collection of molecules escapes through a small hole into a vacuum is called effusion. In both of these cases, the faster the molecules are moving, the faster the rate of diffusion or effusion. This one is just a little easier to do in the lab and control, and therefore that's how things were measured. So diffusion and effusion both occur more rapidly for molecules with higher velocities. And the law is actually called Graham's law of effusion. It is also related to diffusion as well. Here is the law. It says rate of effusion of gas A divided by rate of effusion of gas B is equal to the square root of the inverse of their molar masses. So that means that the molar mass of gas B is going to be in the numerator, and the molar mass of gas A is going to be in the denominator. That's right, B on top, A on the bottom. Like so. And we can do one sample problem which says how much faster will oxygen diffuse than argon. So to get something, and this how much faster, this is going to be, the answer is going to be the rate will be faster. So if the rate is faster, yes, it will have a faster rate. Let's go ahead and plug this in. Rate of effusion of oxygen. And it says diffuse here, but remember this gas law works for effusion and diffusion. Rate of diffusion of oxygen divided by rate of diffusion of argon is going to equal the molar mass of argon And I have misplaced my periodic table. There it is. Argon 39.95 grams per mole divided by oxygen 32.00 grams per mole means that, let's divide this out. 39.95 divided by 32, square root it. 1.12 is the numerical answer, and I don't know if they're units. I would consider them units. So 1.12, where the answer would be oxygen diffuses 1.12 times faster than argon.